Okay, so we're going to talk about the connection between work and kinetic energy. And to illustrate this, first, let's lay out what kinetic energy is. And I'm just going to plop down a definition here. Kinetic energy, I'm going to mostly use the symbol, let me grab a different color here. Mostly going to use the symbol Ke, just so it's very clear what it is. Ke equals 1/2 mv squared. And you'll notice that the kinetic energy of an object is dependent on its mass and also on the square of its velocity. Well, its speed, okay? The magnitude of its velocity. So velocity, magnitude, right? Okay. And I think this makes intuitive sense. You would expect a car that's moving at 60 miles an hour to have more energy conceptually compared to a car that's moving 20 miles per hour. You might not realize that the 60 mile per hour car, assuming it's the same mass as the other one, has 9 times the amount of kinetic energy. So in other words, the energy associated with its motion, and the one going 20 miles per hour, because it's 3 times the magnitude of the velocity. So since that goes as the square, you get 9 times the kinetic energy for that 60 mile per hour car over the 20 mile per hour car. Okay, but that's the definition of kinetic energy, okay? And we've mentioned already that the idea of work is that it is a transfer of energy either to or from an object utilizing one of these forces that we've talked a lot about at this point in the course. Now, there are certainly other ways to do work on objects, right? This is sort of mechanical work done by forces, and you can talk about chemical work and all sorts of other mechanisms for transferring energy from and to an object or a volume of gas or something like that. You get into a little bit of that in chemistry, if I'm not mistaken, okay? But let's formalize that connection, because you can imagine that if you're doing a bunch of positive work on an object, that you might expect it to start moving faster and faster and faster because you're adding to its energy. And that, of course, is going to tie in somehow, right, to the amount of kinetic energy that object has, whether it's gaining kinetic energy, whether it's losing kinetic energy, all of that kind of stuff. So let's use a simple example to show this. And I'm just going to take an object. I'm going to say that at time 0, it's moving with some initial velocity this way. And we're going to apply a net force, okay? And I'm going to call it the net force because at this point I'm just going to say that it's the only force acting on there, okay? But normally we don't put net forces in our free body diagrams. And then at some later time, right, it's going to have some final velocity, and it'll still have that net force on it, right? Whatever force that is, could be somebody pushing it. And we're going to say that's the only force acting on this object, okay? And of course, during this period of time, the whole thing goes through a displacement, starting here, ending there. Sorry for the not quite straight line. We'll call that displacement D to line up with the symbol we've been using in our definition of work. Okay, so where do we start? Well, let's start by saying, well, what's the net amount of work done on this object? We can say that it's the net amount of work because there's only one force acting on it. That's F net, okay? And we're going to multiply that by the magnitude of the displacement vector. And we're going to multiply that by cosine of the angle between them. But what's that angle? Well, it's just 0, right? So this whole thing, cosine of 0 is +1. And so we're left with the net work being done on this object. So the amount of energy being transferred to it or away from it is the magnitude of the net force times the magnitude of the displacement. So this is going to be some positive quantity in this example, okay? Though it could be a negative quantity, I suppose, if the displacement was to the right and the net force was to the left, and so we were reducing the velocity of the object, for instance. Okay, now as far as how to connect it to kinetic energy, let's make a substitution. And we can make a substitution based on what we know about situations like this, where we're moving through a displacement and we have a final and initial velocity. All of this should sound very familiar to us. And the equation of motion that I'm going to apply here is this one. And the only slight tweak to the form that we've seen a lot that I'm going to make is instead of calling this delta x for the displacement, I'm going to call it d. All right? No reason we can't change that notation. It's just a different name for the same thing. And if I solve for d in this equation, well, then I get v final squared minus v0 squared all over 2 times acceleration. So if I make that substitution here, we can start getting something that looks more like something that could be connected to the kinetic energy, right? We're looking for masses, we're looking for velocities squareds. We've got some velocities squareds here, as we can see. But we also have this acceleration hanging around in the denominator, right? This net force is going to cause some acceleration, and that must be that acceleration. But wait, what else is equal to something relating to acceleration? Well, the net force certainly is, right? Newton's second law. So mass times acceleration is equal to the net force acting on an object. In this case, the only force, but still the net force. That means we can cancel the accelerations here. And if I just regroup this a little bit, right? We've got the m sitting out front. We've got a 1/2 that multiplies both of these v squareds. And so if we pull it out and then distribute it, we get this. Now this was for a single force, but it actually works for any number of forces. If you think about it, you could have like, a force here, and a force here, and a force there, and a force there, and a force there, and you add them all up, whatever it happens to be, maybe a force there. And if the net once you reduce this whole vector sum, F net is equal to, F1 plus F2 plus blah, 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 okay? You do the vector sum, you get the net force, you plug it into this equation for the work, and the net work done on an object, and you would come to exactly the same result. Okay, so whether we're talking about one force that then constitutes the net force on an object, or whether we're talking about many, 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 many forces on an object that then add up to give you the net force, you still have this connection between the total amount of work done on an object, so the net force, or the net work rather, on an object, being connected to the difference in the final kinetic energy, because you'll note that that's exactly the same as our definition up here, just with a final subscript on the velocity, so final KE, and this one, which is the initial KE. This form should look familiar, right? Final minus initial. And so if we rewrite that in terms of our symbols for kinetic energy, we have the net work done on an object by some combination of forces is equal to the change in kinetic energy of that object. This is known as the work energy theorem, and it is sort of the first version of this that we're going to see, because it turns out, well, as you might suspect, that kinetic energy is not the only form of energy that an object can have. And the net work done on an object is actually connected not only to the change in kinetic energy of an object, but its change in things like potential energy. And potential energy, we're going to get into that in a little bit, though not quite yet. And so we'll stop here with this form of the work energy theorem. I've formalized this on the next slide, so if you're watching the video and you don't like my handwriting, which is probable, okay, you can take a look at the progression as we work through here. Okay, and that might give you a little bit of a nicer look at all of the notation. Okay, but you'll see all the same kind of stuff there. I added a little more detail in the written version in terms of the steps taken, but you see the end result right there. Okay, so that's the connection between the definition of kinetic energy and the amount of work done on an object, so the net amount of energy transferred to or taken away from an object. What we're going to do next is take a look at a quick example using this work energy theorem, and we'll go from there.